So today we're going to begin our formal discussion on heat and thermal energy. Remember, if you know it, you don't have to write it down. If it's something new, you should write it down. This is the definition of temperature, and this you should write down because it's usually on any quiz or exam or on the Regents. It's the measure of the average kinetic energy of particles. So when we take the temperature of something, we're actually measuring kinetic energy, which is energy of motion of the particles. So the energy associated with the particles moving. When particles move, they collide faster, and when they collide, they increase their energy, thus their temperature. And the opposite can also happen. When particles move slower, there are less collisions, so the temperature decreases. Now, temperature is different from heat. Heat is the total energy in a sample of particles. It has the unit of joule. And on the back of your reference table in Table T, they will refer to this when we use the formula Q equals MC delta T. Q is a variable that means heat, and heat is measured in joules. It can also be measured in calories if we're using the metric unit. So when we talk about energy moving, we have to consider two things: the system and the surroundings. The system is the part that contains the experiment. Is it something dissolving? Is it something melting? The surroundings is everything else. So for example, if I took a chemical and I put it in a beaker of water, and that beaker of water was at standard temperature, say 22 degrees Celsius, which is standard, basically room temperature, and I put my chemical in the beaker and it dissolved, and the temperature decreased. The temperature of the water decreased. That means the system, that chemical dissolving, was absorbing energy from its surroundings. Let's see if I can draw a little picture to help out with that. Don't laugh at my drawing. So here's my beaker. Okay, it's filled with water, and here's my salt, and it's dissolving. And we know that initially the temperature of the water, so we'll call this T1, is equal to 22 degrees Celsius. And as my salt dissolves, right, as it's dissolving into the water, it's dissolving, the temperature starts going up, so that when I'm all done, okay, we can no longer see my substance, but when I revalue, because it's dissolved, right, my T2 is now 35 degrees Celsius. So what happened? Well, in the dissolving process, energy was absorbed by the salt. Energy was absorbed. And where did that energy came from? It came from the surroundings. It came from the water. So the system is salt or chemical dissolving. The beaker, the water, the room that it's in, everything else is the surroundings. So, the system, the experiment, the surroundings, everything else. The first law of thermodynamics tells us that energy can be neither created nor destroyed. So this is the law of conservation of energy. Energy is only rearranged from one form to another. Now this might sound vaguely familiar because we just learned about the law of conservation of matter. Matter can't be created or destroyed. It can only be changed from one form to another. So in this case, energy, the total energy, remains the same before and after. But it can go from the system to the surroundings or from the surroundings to the system. But the net should always be the same. So when we talk about the law of conservation of matter, if I have two reactants, reactant A, 25 grams, reactant B, 25 grams, and they form a compound AB, that compound is going to be 50 grams. It's now on the compound as opposed to two reactants, but my net before and after is the same. And it's the same thing with the energy. It's just going to go from one system, meaning the reaction system, to the surroundings, or vice versa. The second law is heat flows from an area of high temp to an area of lower temp. So I think I've used this example in either this class or another class. I know I've said it a couple of times already this year. But if you have an injury has heat in it. So what do? You get an ice pack. You put an ice pack on it. And after 20 minutes, your leg is cold and the ice pack is getting warmer. Why? Well, your leg is not cold because you put the ice pack on it. That's what everyone thinks. Your leg is cold because heat traveled from your injury to the ice pack, leaving your skin cold. And the ice pack is warmer because it absorbed that heat from your injury. Heat will always flow from an area of higher temp to an area of lower temp. Another example of this is standing in front of a fire. Your body warms up. Why? The fire is hot. So the heat from the fire is going to be absorbed by you because you are at a lower temperature. So now we have to get into some vocabulary terms. One is specific heat. Specific heat is defined as the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree. And every substance has its own specific heat capacity. And you'll know exactly what I'm talking about because I'm sure most of you have been to the beach. I can walk on the boardwalk in bare feet, which is wood, and it doesn't really bother me. And then I walk down on the beach where the sand is. And within 2 seconds, the soles of my feet are burning hot. And I want to quick get to the water. And the water cools them down. Well, why is that? So I started on the boardwalk where it's wood. The specific heat of wood is 1.760 joules per gram per degree Kelvin. Then I said I went to the sand and my feet started burning. Well, the specific heat of sand is less than 1. It's 0.670. And water is really high, 4.18. So what that means is that it only takes 0.670 joules per gram to heat sand up 1 degree. So the sand is going to get hotter quicker. So I could walk on the wood, right? Because that's more than double than that of sand. And then the water is really high, 4.18. So it takes a lot of energy to change water 1 degree. But here's the thing. Sand heats up quick, but it'll also cool down fast when the sun goes down. Water, on the other hand, right, takes a lot of energy. So once it's warm, it won't cool down as fast. So specific heat can have units of joules per gram Celsius or joules per gram Kelvin, which is what I just showed you on the other page. Most of the time in this class, we're using joules per gram Celsius in the heat problems we'll be solving. And I don't think you have to write this last thing down because you just saw that in my example, that specific heat is different for every single substance. And you don't have to write these down either. The only one that you might want to write down, and you really don't have to, is water. It's 4.184 joules per gram Celsius or joules per gram Kelvin. It's also on the front of your reference tables in table B. It's a constant. But you can see here the difference between the substances and their specific heat. So metals are going to have very low specific heats. They're going to heat up really fast. So I'm not sure what happened when I put this into my recording app, but the formula got messed up. So let me rewrite the formula here. It's Q equals MC delta T. And this is on the back of your reference table. So Q is equal to heat and this is measured in joules, Joules. Your M is your mass. Your C, we just talked about, is your specific heat. And T, delta T, I should say, let me put this in parentheses here. Delta T is change in temperature. So this is T final minus T initial. Now, I do want to add that our Q, which is our heat, can be negative if it is exothermic, meaning heat is released, or it can be positive, which means that it is endothermic. And that means heat is absorbed. Okay, so let's do some practice problems. If a pool of water has a mass of 2.25 times 10 to the 7 grams, so there is my M right there. I'm going to mark that. And is outside when the temp is raised from 15 to 37. So there's my TI, T initial, and my TF. How much heat, so I have to find Q, will the water absorb? Now, remember, we're using the formula Q equals MC delta T. M is our mass, and this is 2.25. I'm just going to put E instead of times 10 to the 7th grams, times C, which is our constant, 4.18 joules per gram Celsius, times our change in temperature, 37 minus 15. So I can do that over here. TF minus TI is 37 minus 15, which is going to give me 22. So that's 22 degrees Celsius. So this is a simple multiplication problem. So I get Q equal to 2.069 times 10 to the 9th. And that is joules. So 2.25 times 10 to the 7th times 4.18 times 22 is going to give me 2.069 times 10 to the 9th joules of heat absorbed. Here's another example. If a 100-gram sample, so that's my M, of water absorbs 1,500 joules, as soon as I see joules, I know that that's my Q. How many degrees will the temperature rise? So I don't know my delta T. I don't know what my change in temp is. So let's start. Q equals MC delta T. Now, I don't know how good everybody's algebra skills are, so I'm going to rearrange the formula first. I need to find delta T. So let me put a square around delta T. I need to get delta T by itself. So most of you have learned PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction. So we don't have any parentheses really. We have no exponents. We do have multiplication. The opposite of multiplication is division. So MC delta T are all multiplied. So we're going to divide both sides by MC. Now my MC cancels, and I'm left with delta T equals Q divided by MC. So now we can solve. So delta T equals my Q, 1,500 joules, divided by M, which is 100 grams, times 4.18 joules per gram dot Celsius, which is from table B. Notice my joules are going to cancel. My grams are going to cancel. And I'm left with Celsius, which is what I want because I'm looking for delta T. So my delta T is equal to 3.59, or approximately 3.6 degrees. That's how much it rose. Okay, so you'll get some practice with those types of problems in a little while. We're going to talk about phase changes, melting, solid to liquid, right? Melting is solid to liquid. Freezing is liquid to solid. Boiling is liquid to gas. Condensation, gas to liquid. Sublimation, solid to gas. Skipping, the liquid phase. Deposition is the opposite, gas to solid. So you do have to know your phase changes. So remember, earlier I said when we increase temp, we increase particle motion. Particles move faster, they collide more. So we increase the average kinetic energy of the particles. So what happens when particles are moving faster is that it breaks the intermolecular forces of attraction holding the particles together. And then they gather enough energy and they can go from the solid phase to the liquid phase. Now the opposite's going to happen as the temperature decreases. Particles will be moving slower, so the forces of attraction increase. And they become more strongly attracted to one another. So first we're going to look at a heating curve, and this is when a substance goes from a solid state of matter to liquid and then to gas. During the phase change, which is melting or boiling, which is right here, this line and this line, there is no change in temperature. So temperature is constant. So we said, we defined temperature as the average kinetic energy of the particles. So when I have a change in temp, so right here, I have my kinetic energy increasing. And I also have my kinetic energy increasing here. So anytime there's a change in temp, my kinetic energy is increasing. You're increasing temperature, particles are moving faster, they're going to collide more. At my plateau, where the temperature is constant, at that point, my potential energy is increasing. Remember, potential energy is stored energy. So and this is how you remember it, plateau begins with P. Potential energy begins with P. So at the plateaus, the potential energy is increasing, and on the slants, where the temperature is changing, the kinetic energy is increasing. So we just talked about when temperature changes, and we did a couple of problems, we use Q equals MC delta T. But at the plateaus, when the phase is changing, there is no change in temperature. So we have to use two different formulas. One is called Q equals MHF. So again, Q is your heat. So Q is your heat, and this is measured in joules, just like it was for our previous problem. M is our mass. And H and on ours it says HF. On our reference table it says Q equals MHF, is our heat of fusion. So fusion happens when something is melting or freezing. So I got distracted, sorry. If we're on a heating curve, we're absorbing energy. So it will be a positive value. And if it's a cooling curve, freezing, then it would be a negative value. So recall earlier that I said specific heat was the amount of energy needed to raise 1 gram of a substance 1 degree Celsius. So now we have heat of fusion. So heat of fusion is the amount, and I'm going to abbreviate amount, of energy, big E, needed to change, delta means, the triangle means change, 1 gram of a substance from solid to liquid, or if we're going downhill, liquid to solid. We also have another formula, very similar to that one. Q equals mH V. So your Q is the same. I'm not going to rewrite it. It's your heat in joules. M is your mass. This time, HV is heat of vaporization. So this is the energy required for 1 gram of a substance to vaporize, meaning to go from a liquid to a gas, or it could go from a gas to a liquid. So remember on our heating curve, right? Just going to show you so there's no confusion. Here is where I use Q equals mHV. Here is where I use Q equals mHF. And to make it easier, at A, B, and C, I'm going to use Q equals MC delta T, because that's where I have the change in temperature. So HF, HV, and C are all constants found in Table B on the front of your reference table. You don't have to memorize them. And the formulas, all of them, this one, and this one, are all found in Table T on the back of the reference table. So let's problem solve. If 36.5 grams of a solid, of solid water, why can't they just say 36.5 grams of ice? Be a lot easier. There's your mass. Are melted. So that's a plateau to form heat. Oh, how much heat is absorbed? So just very quickly, if we're looking at our heating curve, right? Solid, liquid, gas. Melting takes place here, solid to liquid. So we're using Q equals mHF. So we haven't talked about what HF is. I'm hoping that you've looked at your reference tables. So Q equals 36.5 grams times H sub F, heat of fusion, is 334 joules per gram. So my grams are going to cancel. And I get Q equals to 12,191 joules. All right, let's look at another problem. If 50.8 grams, so there's my mass. Notice how I always read the problem and I write next to it, of water vapor are condensed to form liquid water, how much heat is released? So condensed means I'm going from a liquid, a gas to a liquid. So here's my gas, liquid, solid. So look where I am now. I'm right here. Condensed, I'm going from gas to liquid. So I'm no longer using Q equals MHF. I'm using Q equals MHV. So my mass is 50.8 grams. My HV is on the front of my reference table. It's 2,260 joules per gram. So my grams are going to cancel. And I get Q equal to 114,808 joules. And this was released. If I don't write the word released, I would have to put a negative sign in front of it because it's exothermic. So that is the end of the notes. Remember, uphill is endothermic, which means energy is absorbed. So this is going to be positive. And downhill is going to be negative because it is exothermic. So energy is released. Okay, I am going to leave you to your practice. If you have any questions, you can still message me. I'm in the building. I will be back and forth, and I will try to stop in and see you at some point in time. Boys, and you know who you are, be good. Don't give my tennis diva a hard time.